Okay, the next thing is radioactivity. So actually, this is the phenomenon of spontaneous emission of radiation. So that means in radiation means they will emit alpha, beta, and as well as gamma by certain nuclei. By certain nuclei called as radioactivity. So actually, in order to understand the radioactivity, we need laws of radioactive disintegration. Laws of radioactive disintegration. So first one we are taking the first law. Radioactivity. Radioactivity is nuclear disintegration phenomena. Nuclear disintegration phenomena. It is independent of all physical. All physical means all external conditions like pressure and temperature and geographic conditions. All physical and chemical conditions. All physical and chemical conditions. For example, second one we are taking, and second law is it is a random process. It is a random process. So that means we can't predict which nuclei is undergoing disintegration. So therefore, it is a matter of choice. It is a matter of chance for any atom. To disintegrate first. So that means if we have 100 atoms, let us say, so we can't predict which atom is going to disintegrate. Maybe the first atom will undergo disintegration, or we will say the 100th atoms also having equal chance to undergo disintegration. So we can't predict which atom is going to be disintegrated or decayed. And so it is found that the third law we are taking. So the rate of decay of nuclei, is directly proportional to number of active nuclei. Active nuclei means undecayed or undisintegrated. So as this is the decay, we are taking minus dn by dt. Minus means it indicates decay, and dn by dt means rate of change of number of nuclei. is proportional to n, or we will take dn by dt is proportional to minus n, or we are removing the proportionality dn by dt equivalent to minus n lambda, minus n lambda. So here we will take the dn by dt. So the dn by dt is the rate of disintegration. We used to call this is the rate of disintegration. Rate of disintegration. And simply we will say lambda is decay constant. Lambda is the decay constant or disintegration constant. Decay constant or disintegration constant. So after taking this, so simply we will write dn by n equivalent to minus lambda into dt. So both sides we will take the integration where the number of nuclei has been changed from n02 to n, and minus lambda into both sides we will take integration right from 0 to t. So if you observe the time from 0 to t, the number of nuclei changes from n0 to n. So we know that integral 1 by x into dx is equivalent to log x formally. Integral 1 by x into dx is equal to log x. So therefore, we will write log n within the limits n to n0 equivalent to, we will write minus lambda into t within the limits t to 0. So then we will write log of n by n0 equivalent to minus lambda t we are getting. And the n by n0 equivalent to, actually this is log base e equal to minus lambda t. Log of base e n by n0 equal to minus lambda n0, or n by n0 from the logarithmic rules we will write it is e power minus lambda t, or n equivalent to, we will write n0 into e power minus lambda t. So first we will understand what the terminology of n and n0, and later we will calculate the graph. So here capital N means number of active nuclei, number of active nuclei, number of active nuclei at time t, number of active nuclei at time t, or we can call it as number of nuclei undecayed, number of nuclei undecayed, and we will call it as number of nuclei undisintegrated, number of nuclei undisintegrated. And we will see n0. N0 is nothing but number of nuclei undecayed, number of nuclei undecayed at time t equivalent to 0, at time t equivalent to 0. And n0 is the number of nuclei undisintegrated at t equivalent to 0. And then now we will see the graph between n and t. So as this is the exponential decay, so therefore I am taking n here and t here. So as this is the exponential decay, so therefore I am taking the graph like this. So n and t. So this graph is important. This is exponential decay. Here it is. N equivalent to n0 into e power minus lambda into t. N equivalent to n0 into e power minus lambda t. Here it is. And here we will take the probability of, next we will take probability probability of survival, probability of survival of nuclei, probability of survival of nuclei in time t, probability of survival of nuclei in time t. So we will take that as n by n naught, probability of survival of nuclei n by n naught equal to e power minus lambda t, minus. So next we used to think of number of nuclei, number of nuclei decayed, and that is n dash equivalent to n naught minus n. Original number minus final active number. So that equivalent to n naught into 1 minus e power minus lambda. And now we will tabulate a graph between the n and t. And this is n dash, and this is let us say this is the original number not. So this is the exponential growth. Actually, we will call this as the exponential growth, exponential growth graph, and we will call the earlier as the exponential decay. So this will be exponential decay. So we will call this is the exponential decay. So these graphs are very important. And next we will see the probability of nuclei to disintegrate, the probability of nuclei to disintegrate in time t. In time t we are taking. So therefore we will take n dash by n naught, n dash by n naught equal 1 minus e power minus lambda. So these things are very important in understanding the problems. Okay. So after that, we will see activity. Activity of a radioactive substance. Activity of a radioactive substance. Activity of a radioactive. So then, so we already learned the activity of a radioactive substance. The activity of the radioactive substance. Generally, we used to symbolize it as A equivalent to minus dn by dt, A equivalent to minus dn by dt, or that equivalent to n lambda. So simply we will write A equivalent to n lambda. So we used to call the activity A equivalent to n lambda, where A is the activity, n is the number of active nuclei at that time, and lambda will be the decay count. So therefore we will write A equivalent to n means already we know n naught into e power minus lambda t into lambda. Or else we will take A equivalent to lambda n naught into e power minus lambda t. Or simply we will get A equivalent to A naught into e power minus lambda t. So this is another principle regarding the activity. So this is another principle regarding the activity. So now again we will understand that. So the A naught and the A also in the name. A naught is the activity. A naught is the activity at time t is equivalent to 0. and A is the activity. A is the activity at time. A is the activity at time. So here we will think of the units for the activity. We have becquerel. So the becquerel is SI unit. So 1 becquerel equivalent to 1 dps. So dps means disintegration per, and also we will take Curie as the CGS unit. 1 Curie equivalent to 37 gigabecquerels. So giga means we know that it's 10 power 9 disintegrations per second. And the activity per unit mass or per unit volume. The activity per unit mass or volume is known as specific activity. Is known as specific. So afterwards, after then we are taking half-life. T-half, we used to call it as T-half. So this is the time in which one half of initial radioactive substance, is decayed, or we used to call the decayed in another words as disintegrated. So now we are going to prove the relation for the half-life. N equivalent, we know that N equivalent to N naught into e power minus lambda. N means active number of nuclei at this instant. So let us say at this instant it is half of the original value. Simply we will write N naught equal to e power lambda. Because so in the time equivalent to T half, so the number of nuclei present in the sample becomes naught by 2. So therefore, we will get 2 equivalent to e power lambda into that time, 2 equivalent to e power lambda into that time becomes T half. So therefore, I will take this as lambda into T half. And by applying the log on both sides, log to base E is equivalent to log to base E is equivalent to log of e power lambda into T half. So we know that log to base E, or it is called as ln2 equivalent to lambda into T half. Or we used to get a relation T half is equivalent to ln2 by lambda. So ln2 value already we know this 0.693 by lambda. So this is ln2. So this is very, very important relation here. So half-life. So already we know this lambda is the decay constant here. And now we will see what happens after n lives. So this is important for problem game. After n half-life. So that is T equivalent to n times T. So now we are going to get similar expressions as so we can write n equivalent to n naught by 2 power n, or we will take the same relation in the terms of activities A equal to A naught by 2 power n, or we will take mass of the sample m equivalent to n naught by 2 power n. So these are very famous relations, and on these basis only we have problems. M equal to n naught by 2 power n, and this A equivalent to A naught by 2 power n, and this n equivalent to n naught by 2 power n. So we know already about n and A. So we need to learn about m naught. M naught is, let us say, initial mass of sample, and m is the present mass. The present mass means, let us say, at t, at time t of the sample. So we are learning all these things for sample. And next, these are very important. These are very important. So this principle and this principle and this principle are very important for problem solving. So where we used to relation small t is equivalent to n into d. So these four boxes are very important for radioactivity. And as we know, this n equivalent to n naught into e power minus lambda. Suppose if we apply the logarithm on both sides, we get log n base c equal to log n naught base c plus log e power minus lambda t. So finally, we are having log n base c equal to minus lambda t plus log. Now we will see the graph between log n and t. So now I am taking a graph between log n base c. So this is a straight line. So because it is in the form of y equivalent to mx plus c, and that slope is negative, so that's why we will get the graph like this. So this is log n and time graph. So after learning this, we will think of mean life, mean or average life, mean or average life. So let us see. Let n be the number of nuclei, n be the number of nuclei at time t, and between time small t and t plus dt, dn number of nuclei are decayed. dn number of nuclei are decayed. So then we will write mean or average life. Mean or average life. The symbol is called as tau. It is pronounced as tau. Tau equivalent to, so integral n naught to 0 into t into dn by integral n naught to 0 dn. So after taking the appropriate integration and applying the limits, you will get tau is equivalent to 1 by lambda. So this is very fabulous relation between the mean life and decay constant. And already we know the lambda equivalent to, already we know T half lambda equivalent to 0.693 by T half, 0.693 by T half, lambda equal to, or we get tau is equivalent to 1 by 0.693 by T half. So therefore, so finally we get tau is equivalent to 1.44 into T. So this is an important relation between the mean life and life. This is very tau equivalent 1.44 into T. And for the advanced, this is important. The upcoming is parallel radioactive disintegration. Parallel radioactive disintegration. Parallel radioactive disintegration. Okay. Suppose we have a radioactive nuclei A, which decays into DNC simultaneously. Simultaneously it will decay, assuming that N0 is the initial number. N0 is the initial number of after time t. So that means decaying process has been started. So we are taking the number of nuclei of A left is Na, and the B formed A is converted into B and C. So B newly formed is NB, and C newly formed is NC. So simply we will say that the original number N0, the original active nuclear number N0 equal to, right now some are left as A and some converted into B and some converted into C. So let us take this as A is converted into B and C simultaneously with the parallel disintegration with respective decay constants lambda 1 and lambda 2. So when we take the differentiation of this N0 equation, dN0 by dt is equal to dNA by dt plus dNB by dt plus dNC by dt. So N0 means this is a constant number. So therefore dN0 by dt equal to 0. And we will take dNA by dt, the rate of decay of A. And the rate of decay of B is nothing but we will write it as activity. So with respect to the lambda 1, and we will take dNC by dt also, we will take it as lambda 2 into dA. And finally, we will write d minus dNA by dt equal to lambda 1 plus lambda 2 into Na. I'm writing the LHS as lambda effective. We are calling lambda effective into n because activity equal to lambda into n. Already we know that minus dn by dt is equivalent to n lambda. So we will write lambda 1 plus lambda 2 into n. So by comparing this, We will let lambda effective equal to lambda 1 plus lambda 2. And already we know that lambda is inversely proportional to 1 by tau, and it is directly uh, lambda is inversely proportional to 1 by t half, that is directly proportional to tau. So we will write so therefore we have t half effective half lifetime. Effective half lifetime is equal to, so because they are inverse relation, so we are taking t1 into t2 by t1 plus t2. We are taking t1 comma t2 are the half lives. T1 comma t2 are the respective half lives. Or we will take the we will take the effective mean life, that equivalent to tau 1 tau 2 by tau 1 plus tau 2. And we will understand all the relations. And this is also we are having similar relation 1 by tau itself, because tau equivalent to 1.44 into t half, and we have relation tau is equal to 1.44 into t half. And this is the very important parallel radioactive disintegration. After this, so we will learn after what happens when alpha particle is decayed. After alpha decay, what happened to the parent nucleus? So we are taking this when alpha particle, so that is helium nucleus, decays when alpha particle, that is helium nucleus, decays from a parent nuclei. Let us say its name is ZX2. Then its atomic number, that is Z, decreases by 2 units, and mass number, capital A, decreases by 4 units. So let us see one example. If I am take ZXA gives rise to an alpha particle. So we are taking this 2 helium-4 as alpha. When alpha particle is emitted, its atomic number is reduced by 2 units and mass number is reduced by 4 units. So we will take Z minus 2 by A minus 4. Then simply we will say this X is called as parent nuclei and Y is called as daughter nuclei. And Y is called as daughter. So now I'm going to see one example for this. Suppose if you take 92 uranium-238, when it emits an alpha particle, 2 helium-4 means so it is nothing but alpha particle. So we studied that mass number decreased by 2 units, that is 92 becomes 90, and we will get a new element, thorium, and mass number decreases by 4 units, that is 90 thorium 34. Okay, and alpha particles are generally emitted by a nucleus, to get stability. To get stability. So the energy available in this process, available in this process is, so here what happens, x becomes y and alpha. Okay, so in this process q energy, we will call it as q energy, that is mass of x minus mass of y minus mass of alpha. So the productant mass minus the reactant mass minus productance into c square. So this q energy. So that means that when we have some mass differences between the uh, reactants and as well as productants, this x is called as reactant and the y and alpha are called as productants. This energy, this is called as q energy. This energy appears in the form of kinetic energy of products. So that means it may appear in the form of kinetic energy of alpha particle, the above example, and as well as thorium. So here for a while we will discuss about q value of nuclear reaction. Q value of nuclear reaction. Suppose if a reaction is given as x plus a gives rise to y plus b, so then q equivalent to just now we discuss mass of x plus mass of a. So x is one unstable nuclei and y is a stable nuclei. A, B are the particles we will use. Ma minus Nb minus Nd into c square. If Q is equivalent to positive, we will call that as exothermic. And if Q is equivalent to negative value, so then we will call it as endothermic. So this is about Q value. So after discussing about this, we will think of beta decay. What happens when a beta is decayed? So here we are having three kind of beta particles: beta minus, beta plus, and beta 0. So first we think of beta minus. Beta minus is nothing but an electron. So here when number of neutrons are large, so to get stability, that neutrons converted into protons. Actually, we have discussed in the earlier. So this is called as Yukova-Meson theory. So that means when a neutron converted as proton, we get an electron which is associated with antineutrino. So we used to call this as antineutrino. So when electron is released, so definitely to satisfy the conservation of spin, we will use antineutrino. So or else I will take one more example. Suppose if I take a parent nuclei ZXA, so it gives an electron like this, -1v0. Electron is always associated with antineutrino. So then we will get a daughter nuclei with chemical name Y. So here we will see that one atomic number is reduced actually. So that means that from the parent nuclei to daughter nuclei, atomic number has to be raised. ఎందుకంటే Z conserve అవ్వాలి కాబట్టి Z becomes Z plus 1. and the mass number remains unchanged. The mass number remains unchanged. So, or we will write the same equation as ZXA gives rise to minus 1 is 0 is called as beta minus plus anti-neutrino plus Z plus 1 into pi into 2. So that means what is the logic here is when beta minus emitted, its atomic number increased. Atomic number means Z increased by 1 unit. Whereas no change in mass. No change in mass. So similarly, we have beta plus decay. So I'm taking the basic kind of example. So when a proton gives rise to neutron, we get the positron. We have decay. So simply this beta plus particle is nothing but it is called as positron. Positron means this is anti-particle of. So we are taking another example. If we take ZXA, it gives rise to one positron. So you need to remember that, like electron, the positron is always associated with the neutrino. Nu means we will call this as neutrino. To conserve the spin, we are taking like this, and we have the data y z minus a, and this is a. So clearly, we will see that from here is when beta plus is emitted, its atomic number Z, we have seen that reduced by 1 unit, whereas no change in mass. Whereas no change in mass. Okay. So finally, what is your conclusion? Is in beta decay the mass number is, and ultimately you are speaking about the gamma decay. So in the gamma emission, so the mass number and atomic number both remains as constant. So here what happens is, like the electrons, the nucleus also having excited levels. So excited levels and as well as ground levels. So here we will see. So that means whenever a nucleus will fall from excited state to the ground state. So you need to be understood in a way that the star indicates excited state, and this ZXA means the nucleus is in ground state. So this ZXA, we are speaking about the excited state of nucleus to ground state of nucleus. So when a nuclei will jump from excited state to ground state, we have automatically energy emitted in the form of gamma. But the basic difference between the electrons and as well as nuclei is, generally we know that for electrons, energy is in the order of electron volts. Energy levels having energy in the order of electron volts. But for the nuclei, we have energy levels in the order of mega electron volts. In the order of mega electron volts, we have